A particle travels on the parametric curve, and it's given by e to the 2t in the first coordinate, 2t e to the t minus 2 e to the t in the second coordinate, and 1/3 t cubed in the third coordinate. Find an at 0, and we have options. They're basically 1, 2, 3, 4, or 5. Those seem to be popular choices for the problems we write. What's the answer? Someone has said C. And, well, it's good that they said it. You know, that gets us going. It was B. It was 2. Okay, so as we mentioned, this type of material is fair game. Now, usually they don't put it in multiple choice because it's hard to put these kinds of problems in multiple choice. But it's absolutely fair game for the exam. So remember, what's the process? Well, if you want to find your A sub n, well, you have to remember what it means. It's about acceleration. So you're decomposing acceleration, so you're probably going to have to find acceleration. So you find r prime, velocity r double prime is this acceleration. You find the magnitude of r prime as a function of t, and then the fun begins. First you find the tangential part, which you say, okay, that's the derivative of magnitude of r prime, which would be 4 e to the 2t plus 2t. Now, if you try to plug in t equals 0 here, you get 4, but that's not the right answer. Now, why did I plug in t equals 0? Well, so I know I have to plug in 0 at some point. There's always the question, when should you evaluate? And the answer is you should evaluate as soon as possible, but not sooner. Why did I not evaluate here? Because what was my next thing after I had this? Took the derivative, and if the derivative of a number is 0. So I had to wait until after I was done with derivatives until I did the evaluation. But once I was past the derivative stage, at this point I can just plug in 0 to everything. So plug in 0, we get a sub t. Plug in 0 into your velocity, you get the vector whose magnitude squared is 20. Then you have your basic Pythagorean theorem type thing kicking in. 20 is 16 plus your an 0 squared. So an of 0 is 2. All right. Good. So now we'll be ready. If they ask us a question on the test, no problem. So today's thought, you probably looked at it already. I must not fear. Fear is the mind killer. Fear is the little death that brings total obliteration. I will face my fear. I will permit it to pass over me and through me. And when it has gone past, I will turn the inner eye to see its path. Where the fear has gone, there will be nothing. Only I will remain. That's definitely a very mathy quote, isn't it? Oh, wait, no. So, do people know where this comes from? Dune. Okay, yeah. So Frank Herbert was the author of Dune. And, but why did I want to do this one? Well, I probably should have just, the first couple words. I must not fear. Fear is the mind killer. You're going into the exam, and fear, nervousness, those emotions are somewhat natural, but also not helpful. Now, it's easy for me to say, yeah, just don't be nervous. But it's not so easy to do that. So one of the things is you have to learn how to deal with your emotions. You have to know, how do I overcome my nerves? How can I be in a stressful situation and not be stressed out? So a lot of it comes with preparation. The more preparation that you do, the more confidence that you have, the less nervous you'll be. But there's also things such as, there's really breathe in, breathe out. You hear that said a lot. Calm yourself, calm the body. Go through your rituals, whatever they are. If your ritual is going and buying, a big thing of coffee and drinking I have no idea, what passes this big amount of coffee? 20 ounces? Is that a large amount of coffee? Sure, okay. If you want to go grab your 20-inch coffee before you do your test, you do it. You grab your 20-inch thing. No, not 20 inches, 20 ounces. That's right. That's why I can't teach physics. I don't know units at all. That's why. But all right. You do what you need to do. You do what you need to do. All right. Okay, so today, what's our topic? Well, we're going to be moving into functions. And in particular, we have to remind ourselves what functions are. So a function, I like to think of it metaphorically as a machine. I have this machine, and into this machine I will put things into it, and out of my machine I get things out of it. And this is my function machine. Now the only thing that has to be true is that I need to be consistent. So that is to say, if I put a 2 in today, and out comes a 7. And then next week I put in a 2. What needs to happen? I need to get a 7. So a function is just a consistent rule that assigns input to output. So that's the idea. It's very simplistic in this sense. We say, okay, well, what kind of functions can we have? Now, we're used to some functions. Y is a function of x. And we've been hanging out with that for such a long time. That's how we often think of functions. Like I have a number. I plug it in, out comes another number. But that doesn't have to be the only thing that comes in. We can have our input be different things. So for instance, our input can be pairs of numbers. And so we have an example here. Z is a function of x and y. So this is an example of a 2-variable function, because we have two variables being fed into our function. And this is where we'll spend most of our time. And in some sense, we can have a lot more. Like here's an example where we have 3 variables being fed into our function. But why do we do this? Well, because the world tends to be complicated. It tends to be the case that when we are interested in some quantity, it almost never relies on just one thing. It often relies on multiple things. And so we have to have a way to capture multiple different things happening. So that's why we'll have functions of multiple variables. So these are our multivariable functions. Now, I should point out, we can have multiple variables going into our functions. We can also have multiple variables coming out of our functions. And we've actually been doing that. If you think about parametric curves, you can say, well, what happens? Your input is time. And then your output is location, which has 3 components to it. So you can have sort of a higher dimension of input. You can have a higher dimension of output. And so functions are very broad. Now, we're going to do just very simplistic things today to make sure we understand what's going on. The output of our function, we call the range all the possible outputs. So when you talk about the range of a function, well, that's what comes out. Now, range, that's hard. Knowing everything that can come out of a function, that's challenging. But there's another side to the story, which is our input. So if the domain is what comes out, what is the input? Yeah, the domain. And these are all possible inputs. Now it turns out that generally speaking, it's a little bit easier to get a handle on the domain. So what are some things we're going to look for? Well, instead of focusing on where things work, you basically say, let's focus on where things break down. So, possible issues. And more or less, the idea here will be, well, if we avoid issues, then we're good to go. So think about your algebra and arithmetic. What are things you're not allowed to do?
Divide by 0.
Good. Wow. Your algebra teachers are all proud. Divide by 0. Okay, so we say, look, let's avoid divide by 0. We scan and see if there's any place where there's a 0 that shows up downstairs. And if there is, that's out. Can't have it. Okay, what are some other possible issues? Yeah. Square root of a negative. So, can't do that. When you take the square root of something, it has to be something that's not negative. So it could be 0. 0 is okay. Could be positive, but it can't be negative. Not in our class. Now, if you want to take the square root of a negative number, there is another class that you could take. But it gets a little bit more complex. Okay, but anyways, don't divide by 0, don't take square root of a negative. There's one more. Logarithms. Who said logarithms? Or what is it? Okay, yeah, log of a non-positive. Actually, yeah, okay. Let's see, log of a non-positive. Well, we'll say log of anything less than or equal to 0. That's the way you say non-positive. So 0, can't take log of 0. Not going to work. Log of a negative, not going to work. So once you identify your possible issues, for most of the functions that we're going to encounter, also known as all the functions we're going to talk about, the domain is everything else. Now, of course, you can come up with exotic functions. You can maybe have something piecewise, but you figured out your issues. The domain is everything else. All right. So let's try a problem. Here we go. So, sketch the domain of g of xy equals the square root of 2x minus x squared over the natural log of x minus y squared. Now we're doing this one together. Now first off, when we talk about our domain, where is our setting? Are we in a line? Intervals on a line? Are we in the plane? Are we in three-dimensional space? What is our domain? Where's our setting at? Our setting is in the plane. How do we know it's in the plane? Yeah, we have two variables. So we have two inputs. So when we talk about our domain, our answer will be a sketch in the xy plane, because those are our inputs. Okay, so all right, so that's that. So let's start talking about some of our problems. So this one actually has a couple of problems in it. So what's a problem? Let's talk about. Pick a problem. Okay, so we have a square root of something negative. All right, so there's a square root here. So we say, okay, so what do we need? We need to make sure that 2x minus x squared is greater than or equal to 0, right? Because if 2x minus x squared is negative, we're in trouble. Now, if we think about the graph of 2x minus x squared, so we'll draw it here fairly quickly. So 2x minus x squared, what does that look like? Parabola? Is it upside down? Right side up? Left ways? Upside down? Do you know where it hits the axis? 0. Okay. Anywhere else? 2. So upside down hits at 0 and 2. Where am I positive? From 0 to 2. So this is the same as, so need x to go from 0 to 2. Okay. Yes? If x is not between 0 and 2, 2x minus x squared is negative, and that's not going to work for our function. Okay, so that tells us something. It tells us the following. We can sort of say, okay, this tells us that there's this line x equals 0, there's this line x equals 2, and I've drawn them with a solid line deliberately because we're going to include it. So solid line, I should have mentioned this, so we'll put it here. A solid line equals include, and a dotted line equals don't include. So there's sort of things on the edge. So notation. Oh, also a circle also equals don't include. All right. So there we go. We've taken care of the square root issues. Are there any other problems that we need to take care of? Okay, I've got to take care of the logarithm. All right. We'll work on that one. So what do we need? We can't take log of anything less than or equal to 0. So that tells us what? We need the inside of the log. X minus y squared has to be positive. Okay. Well, that says we need x to be bigger than y squared. Yes? What does x equal y squared look like? It's a what? A sideways parabola. What? To the side? That's crazy. But which side? Am I opening in this way, as I seem to have suggested by the way I drew my axes, or am I opening this way, which doesn't seem to work with this picture? The first one, right? Okay, yeah. So it's a lot like y equals x squared. It's just on the side. And notice it's a strict inequality, so we're going to use dotted lines. That's really not a solid line. It really is dots. There's dots. Okay. Question. Am I in this part or that part? The inside or the outside? How can you know? Oh, okay, that's a reason. That's a nice reason. X has to be to the right of y squared. Now, that's a great argument. Here's another one. When in doubt, pick a point that's not on this line. How about this point? X equals 1, y equals 0. And test, does it work? Is 1 bigger than 0 squared? Yes. So that says, hey, I got to include this point. So once you know I include this point, it's like, okay, I got to include all these points. Because you have to fill it up to the boundary. Okay, so you also have this condition. All right. Now, both of these have to be true. So you have to sort of like cross your eyes. Anything else?
X minus y squared can't equal 1.
Why can't x minus y squared equal 1?
Because then ln of x minus y squared is 0.
Okay. So divide by 0 is bad. So we can't have log of x minus y squared equals 0. That says x minus y squared can't be 1. So that says x cannot be 1 plus y squared. So what does 1 plus y squared look like? So this is x equals y squared. What does 1 plus y squared look like? Yeah, it's shifted. Do I shift to the left? Do I shift to the right? Do I shift up? Do I shift down? Do I somehow move my pen up into three-dimensional space? It will be to the right. All right. Now, do I shade this time? Why not? Yeah, because notice these are inequalities. So when you see inequalities, that refers to regions. When you have equalities, essentially we're saying x equals 1 plus y squared. That's an equality, and then we're just marking it as bad. You don't shade. All right, so what do we need to do? Essentially, these are our three problems. So what do we do with these three things? Find where they're all true. So we're going to put them all on top of each other. So we'll start doing some sketching. This will be a little bit sketchy here. So we'll be very cautious. We have the x equals 2. And we'll come in and fill things in a second. We'll have the x equals y squared. And here's the x equals 1 plus y squared. All right. Now, we start filling things in. Yes?
Should x equals 2 be a solid line?
It will be. Yes. Or will it? Whoa. What's going on here? So, x equals 2 will mostly be a solid line, but not all of it. What are some problem points? We can't have these points. So those are out. We can't be anything up here. We can't be anything down there. What's wrong with these pieces? They're outside the parabola. So we're going to include those parts. Is there anything else we need to do? Yeah, so we're going to fill in the rest. We have that. And I don't know why I'm being so careful. Because I'm not very good at staying within the lines. You can see I already went outside the lines there. All right. And there you go. That's the domain. So that piece is where all three things are true. All right. Any questions? Cool. Well, in that case, here's one from an exam. Sketch the domain of the following function. Square root of 4 minus x squared plus log of x squared plus y squared minus the square root of 9 minus y squared divide by the square root of x plus y plus 1. Do we have a rough semblance of a picture? And I know you're like, how can you tell us a picture, communicate a picture? Maybe we'll test your geography. What state does it look like? Did you get a picture and say, I recognize that?
Nevada.
Right. It looks like, not Nevada, Nevada. So that's the picture. All right. So you have 4 issues, right? And the upstairs, you just say, okay, the square root of 4 minus x squared. That says you have to have x between negative 2 and positive 2. Similar, square root of 9 minus y squared says y has to be between negative 3 and positive 3. So essentially, you're down to this square. Log of x squared plus y squared has basically no problems except one. And that's at 0, 0. So you have to take out the origin. So there's a hole here. So the last part is the denominator. Well, x plus y plus 1 can't be negative, but it can't be 0 either. Because if it was 0, you'd be dividing by 0. So x plus y plus 1 has to be greater than 0, which says y has to be greater than minus x minus 1. So you have the line, y equals minus x minus 1, and you have to be on that side of the line. So that says that region is what satisfies all the conditions. All right. That was fun. That was fun. Good, clean fun. Something to look forward to in a month. All right. So we need to talk for a little bit about how do we understand functions, and for that, probably a quick reminder of graphing functions. So we have a pretty good idea of how to graph y equals f of x. We've been working with these functions for quite a while. So what we have is we have somewhere downstairs, this is our domain. And then we say, you pick a value for x, you come up here, you put a dot in for the corresponding value for y. So essentially a graph is a collection of points. You put in every single input with corresponding output. Now, what do you do for z equals f of x, y? Well, same kind of ideas. You have your domain somewhere. Let's say this is our domain. And say, all right. Then what happens? Let's see if I can do this. So sitting above our domain, we have now a collection of points. And, well, it might be somewhat more wavy. Okay, so here's it's our surface now. And so what happens is that we say, okay, look, for any point in our domain, here's a point x, y. We go up, and we say there's a corresponding point up here, and this is at our f of x, y. That's our z value, is at f of x, y. And we do all these points. Now, okay, that's great. And if you're very patient, or you're a computer, wonderful. You can do this, no problem. But things can get more complicated. So there's other ways for us to think about what's going on, other methods of visualization. And in particular, we're going to focus on something called level curves. And this also goes by contours. So sometimes you'll hear contours, sometimes you'll hear level curves. And the idea is very simple, is you're going to slice it. So we're going to set f of x, y equal to k. So you can imagine that maybe we have something that looks somewhat like a bowl. And what we'll do is down here we'll have our plane, and now we slice. So we'll slice at some level, say this is z equals 2, and it will intersect that surface. And then what we do is down here in the plane, we put in that corresponding intersection. And then we say, okay, but we can do another slice. And again, it will intersect our surface, and we move it, project it down, and this z equals, say, 4. So we just repeat this over and over again, and what we end up with is sort of these collections of curves. And these curves represent points at the same height. So if you've ever gone hiking, you have like a topographical map, and it indicates elevation of things. And so you can understand the topography. It's a way to store 3D information in a nice 2D format. So that's what's going on with the level curve. For instance, I happened to print out a topographical map of Nebraska here. Not particularly useful, but you can do things, I guess. But so the moral here is that we can understand what's going on with the function by understanding these curves. And in particular, we often will label them so that you can understand how things connect. So level curves, contours, think of these as slices through a function. So we'll do a quick example, do it together here, where it says sketch and label the level curves for the function f of x, y is y over x squared plus 1. And we have various values here given. So what does this ask us to do? Well, it says do the following. You set the function equal to these values. So y over x squared plus 1 equals negative 1. And now you say, this is not a three-dimensional thing anymore. It's a two-dimensional thing. So it can go in the plane. This is y equals minus x squared minus 1. What does that look like? Parabola. Upside down, right side up, left, right. Yeah, it's upside down, shifted down. So this is -1. Okay, so how about -1/2? Y over x squared plus 1 equals -1/2. All right, well, we can think of this as -1/2 x squared minus 1/2. What is that? It's a parabola. It's not shifted down so far, but still opening downwards. Anything else about this parabola? It's kind of wider. Yeah. Okay, I'm really bad at drawing this, but imagine you had somebody who had good technology. All right. What about, say, 0? Y over x squared plus 1 equals 0. What does that say about y? 0. What is that? The x-axis. So there's 0. All right. Well, let's see, how are we doing on time? We'll finish this example, and we have a little bit more to talk about. So y over x squared plus 1 equals 1/2. That is going to become y equals 1/2 x squared plus 1/2, which is a parabola opening upward. This is 1/2. And one last one. Y over x squared plus 1 equals 1. Oh, that's not very dark, is it? Y over x squared plus 1 equals 1. That says y equals x squared plus 1. Ah, that sounds like a parabola we could really get behind. 1. Okay, so what can we do with this? Well, this is supposed to represent a surface up in 3D. So now I'll ask a simple question. I'm in my domain down here. As I move in this direction, what's happening on the surface? So as I'm moving along this, what's happening along the surface? And how do we know that? Well, yeah, it's flattening, but in terms of the surface, if I'm moving from down here to up here, how am I moving? What's my vertical movement? How do I know I'm going upward? Because I'm looking at these level curves. Level curves tell me elevation. If I'm at this level curve, I'm at an elevation of -1. And then I'm at an elevation of -1/2, and then 0, then 1/2, then a 1. So I can figure out my motion upstairs by what's happening in level curves. Am I going to higher values of level curves? I'm moving up. Am I going to lower values of level curves? I'm moving down. What if I move along the axis? What am I doing on the function? I'm constant. Why am I constant? Because I stay on the level curve. A level curve says you're level. You're just hanging around, watching Netflix, not doing anything. So, all right. Cool. Cool. Now that's functions of 2 variables, but we could have functions of 3 variables. And then what do you have? Well, you don't have level curves, you have level surfaces. Now you might say, wait, are we going to have to deal with functions of 3 variables? Yes. How do you visualize them? No, you don't. But you can build up intuition about them. So oftentimes when we think of functions, we think of, like x is our input, y is our output, so it's like a height. But we don't only have to think of height. One of the things that we can think about, for instance, is we could think about like density. Because that's sort of an intuition that we can get behind. I have a 3-dimensional object, and I might have it's composed of some media. And at different points, I'm at different densities. And so this function could be capturing that. So there are ways to sort of get intuition for functions that are multivariable functions, even if you can't do visualization of four-dimensional objects. Okay, some level surfaces of this function, z minus x squared minus y squared. Now it doesn't tell us which ones we should do, so we get to pick our values. So when we're talking about level surfaces, we set the function equal to a constant. So we get to pick a constant. What constant do you want? 0. Okay, so z minus x squared minus y squared equals 0. What is that? What's another way to think about that? Someone said paraboloid. Good. What kind of paraboloid? Be careful, it's not hyperboloid, paraboloid. Z equals x squared plus y squared. What do you see? Yeah, you can be fancy and say elliptic paraboloid, or you could say it's a bowl, Steve. Yes, it's a bowl. I agree. Z equals x squared plus y squared. Okay, what's another level curve? Well, okay, pick another value for what we should set our function to. Z minus x squared minus y squared equals 2. Z equals x squared plus y squared plus 2. What is that? Someone said a bigger bowl. Well, these bowls are all big. I see a hand motion. Yes, we're raising it up. It's a vertical shift up by 2. All right, so we've moved it up by 2. So I guess we could have labeled this. This is 0. This is 2. All right, do we need one more? Nope. Okay, but we'll do it anyways. Z minus x squared minus y squared equals 4. Z could equal x squared plus y squared plus 4. And then that's a bowl, but again, you've moved it up. 4. So what do you get? Well, you get something that you might see at your grandparents' house if you open the kitchen cupboards. A bunch of Tupperware stacked. There you go. That's what it looks like. All right. Now, the last thing for today, we're going to just mention some words. So don't panic about these words. We're not going to test you on vocabulary. So if you don't learn these words, you'll be fine. But we're going to use them from time to time. So the idea here is we have a region. Maybe it came from our domain. So let's say this is our region. It's our set of points. And I'm including this. So we have to have a way to talk about things. So when we talk about the interior, that just says things on the inside. How do you know if you're on the inside? You can say, look, everything near me is on the inside. That's the interior. The exterior are things on the outside. How do you know if you're on the outside? You're on the outside if everything near you is also on the outside. Well, what's between the inside and the outside? The boundary. How do you know if you're on the boundary? Well, you're on the boundary if you look nearby, there's always something on the inside and something on the outside, no matter how closely you look nearby. Now, the boundary could be part of your set, but it doesn't have to be. It could be something that's not in your set. If you have all your boundary points, you are closed. If you have none of your boundary points, you are open. Now, the last idea is this notion of bounded. Bounded basically means you don't get big. I can put you all inside of one big ball. Now, the big moral of calculus, which we don't tell you about, is closed plus bounded equals nice. And so we will often say, if you have a closed and bounded set, you have a very nice property that follows from that. So we'll do a little bit with this, but again, don't worry too much about the terminology. So our last thing for today, in our final minute, maybe 2, let's just check. Here we have a multivariable function. What is the level curve for f of xy equals 2? Did you say C? So the answer is C, because it is a circle. You rearrange it, and you see that it's a circle whose center is at x equals 2 and y equals -1. You mark where the centers would have to be, so I marked them really quickly. Only one of these works with a center of 2, -1. And so the answer was C.